So this week's rock star is Stuart Smith. So Stuart's got more than 30 years of global exploration experience, and I'm so happy that you're joining us today to chat about the evolution of the Porphyry exploration model. So thank you so much, Stuart, for joining. It is an absolute pleasure to have you.
Thanks very much, Jess. I'm really looking forward to this afternoon. Hopefully we can get some good discussion going, because I imagine not everyone will agree with what I'm about to say. Okay, so I'm using the subtitles here on the bottom for the first time, so it will be interesting to see how they interpret my my voice or my accent. I'm a bit nervous, to be honest. So anyway, so what I wanted to well, first up, just very thanks to Jess and everyone involved in the GeoHug initiative. I think it's a fantastic thing that you've done here to bring us together, and I really appreciate being asked to give some thoughts here, and thanks to everyone that's taken some time out of their Friday afternoons to have a listen. And I know there's even some international people, so thanks for taking the time, even depending on what time zones, etc. you're in. So what I want to talk today to you about is, as we said, it's the Porphyry model. And what I want to do is just talk a little bit about how the Porphyry model's changed over time, and particularly then how it has impacted on exploration success over time, and then where we some ideas around where the model might conceivably go in the future. So first up, just I want to make sure we're all on the same page here around what I'm talking about when I talk about a model, because I think some people think of that in a slightly different way. So it's just, simply it's a simplified representation of a system which attempts to describe or explain the system. But in the geological and exploration and ore deposits context, there's a few different types of things that we need to think about, I think. So my definition of a genetic model is one that describes how an ore deposit is created, and the descriptive model is one that describes the key characteristics of an ore deposit class, but doesn't necessarily try to tell us how it formed. The most useful models, I think, for explorationists are what I call simple exploration models. And the difference here is an exploration model, in my mind, is one that tries to predict the location of and how to find an ore deposit. And it'll take aspects from each of the former two, but it's quite a different beast. And most of what I'm talking about today is this piece here. It's around the prediction piece. And in fact, I'm not really going to talk much at all about the detection piece. So if you came here looking for a discussion around the geophysical characteristics of porphyry deposits, sorry, you'll have to talk to Terry Hoschke. So I'm talking very much around the predictive piece here today. And the key question I'm going to be asking, and you probably get sick of me asking it as we go along, is how well does the current porphyry model predict? And so we're going to have that discussion at the end and see what people think. I notice the subtitles are inserting porphyry for porphyry. That could be a challenge for some people. There we go again. So in terms of the structure of the talk here, I've got a couple of slides that I want to introduce around what I call the fundamental heterogeneity, and I think this is absolutely critical in the porphyry world, and I'll explain what I mean by that. Then I'm going to talk about the evolution of the porphyry model over time, and in doing that, I'm going to use various examples of models and iterations of the model. Obviously, in a time frame such as we have today, I'm not going to be able to touch on every paper and every version of the model that's out there. So if your favourite paper or your favourite author doesn't get a run today, don't get angry at me. We can talk about it later, but it's a summary I'm doing here. Then I've got a few slides where I want to talk about how have those models influenced exploration and exploration success over years, and then I'll wrap up with a couple of slides about the future directions and where those models headed and where it can head. So in terms of this concept of heterogeneity, there's two aspects here. There's spatial heterogeneity and temporal, and I'll talk about the second in a minute. But in the porphyry copper world, and I think I'd argue in all ore deposits, but in the porphyry copper world, there's a first order spatial heterogeneity in the distribution copper and copper deposits. And this on the left here is an example from Dick Silito's 2013 contribution, where he looked at the Pacific margin and segmented it by its copper endowment, and this margin has been a broadly permissive margin for porphyry coppers since the late Mesozoic through the Cenozoic. So it's a fair thing to do, I think, is to look at this broad margin and compare where the copper sits within that margin. And of course, no surprise to anyone, excuse me, that there's an extremely heterogeneous distribution of copper throughout that broadly permissive margin, with, of course, northern Chile and southern Peru being the superstars here, with the greatest endowment, and other regions with very little endowment per sort of unit area, if you like. So that's a first order spatial heterogeneity. There's a second order spatial heterogeneity that I think is even more interesting, and this is an example on the right here of Chile itself. So Chile occupies about 0.5% of the world's land surface area, but it contains about 30% of global copper resources. So there's something very unusual, and we all know that. There's something very unusual about Chile. And the enormous endowment of copper that goes to this concept of a second order spatial heterogeneity. And then we can go down even further than that. And within Chile, 75% of the copper in Chile is contained within two regions, and I've outlined them here. So the Eocene and Oligocene of northern Chile from Escondida to Coyahuasi, and then the Miocene of further south from Los Palambres del Teniente, contain about 75% of Chile's copper. So there is the distribution of copper is fundamentally heterogeneous, and a fully integrated porphyry model needs to explain this. And the same applies if we look at the temporal aspects of copper endowment as well. So the two graphs here are ones I've compiled from dated deposits in Peru on the top and the bottom, Chile and Argentina, and the copper endowment within those boxes there. And we can see, as we all know, there's discrete age ranges of the belts in the Andean margin, and the copper is heavily biased towards these short-lived fertile periods within that overall sort of late Mesozoic to present day arc. So there's something very strange going on there as well in terms of the temporal distribution of copper endowment, and our porphyry model needs to explain that. If we drill down even further on the temporal side, we've got those critical 10 million year fertile periods within 100+ million year old arcs. But within those, we've got districts of the order of 5 to 15 million years, so short-lived within the overall arcs. But we've got deposits that typically form within 200 to maybe 1.5 million years. So again, really heterogeneous distribution there. And we've got stages within individual porphyry deposits that probably form within the space of thousands of years, as shown here by really good work at Octetti by Peter Pollard and others recently. So there's something going on in our porphyry environments where we have these sort of 10 million, roughly, less than 10 million roughly fertile periods, and then really short duration triggers within those periods. And a fully integrated porphyry model needs to explain this. And my view is that it probably doesn't explain these very well at the moment, and that's a hindrance to exploration. So what I want to do now is move on and start looking at the model as it's changed over years, and I'm going to take the porphyry model and attack it in from two aspects. So one is at the sort of belt scale, and one is at the deposit district scale. And I'm going to talk about the belt scale first. And the belt scale model and the use of the model at this scale is really an area selection tool. So if we think about our exploration life cycle, here from sort of area selection through to drill target definition and outward into the deposit discovery and resource definition. Our province or belt scale predictive models really have their impact here at this first stage, at this area selection stage. And then our deposit and district models really kick in as we go out into these later stages of exploration and activity. And self-evidently, in my view anyway, if the area selection is poor, your exploration success probabilities will approach zero. And another way to say that is if there is no ore body in your area, then it's impossible to find one. So, and in the porphyry world, area selection is all about predicting those fertile districts within overall much larger and longer lived arc segments. And I think it's this end of the model that we really need to improve. So if we firstly look at that belt scale sort of view of porphyries, and on the top right there, I've just got a snapshot from the Titley and Bean 1980 economic geology contribution that shows the view of porphyry belts at that time. And then the bigger map is the current USGS porphyry data set, which outlines those belts as well. And what we can see, there's very little change there in the last 35, 40 years. Essentially, the belts we knew about in the 70s are still the belts we know about now, with the exception probably of areas in the former Soviet Union, China, and some of the Central Asian regions. And I would argue that their absence in this Titley and Bean contribution, it was largely a function of information flow during the former Soviet Union time. So I think our understanding of and our knowledge of the location of porphyry deposits at the belt scale has really hardly changed at all in the last 35 or 40 years. And probably one big difference would be in our backyard here, down here in the Macquarie Arc, was not as productive and as important then as it is now. So in my view, the exploration challenge in the porphyry world is largely one of getting better within known belts. Probabilities of defining brand new porphyry belts are pretty low, so it's about getting better within those belts. And so what do we know about the controls at that belt scale, and how do we go about predicting where districts might be? And people started thinking about these sort of scale fairly early in the world, in the life of the porphyry research and porphyry model. Dick Silito's 1972 contribution linking porphyry deposits to plate tectonics, which was a relatively new science at that time, was an important contribution. And there were others around this time, but there was a far lower degree of thought and evolution of the model at this belt scale in the sort of 70s and 80s than there was at the deposit and district scale. Another important contribution here being that of Mike Solomon, where he was one to recognise the importance of complexity in subduction margins, and the importance of tectonic triggers to the formation of porphyry deposits. And that's a really important contribution that I think often gets overlooked. And then if we move into the sort of 90s and 2000s is where people, I think, started coming back to this sort of scale of thinking. And we had contributions such as Dave Cook and others here, but a number of other people had made the same leaps here, where they were looking at the influence of the collision of buoyant ridges such as the Nazca Ridge and the Juan Fernandez Ridge in Chile in the distribution of major mineral deposits, causing, by the creation of flat slab segments within the arcs and the cessation of volcanism and putting the arc into strong compression. There seemed to be a control there on the location of deposits, and that was borne out by a number of studies. And including around about the same time in Chile, where people started putting together the understanding of the evolution of the Andean arc and the slab angles and the relative compressive nature versus extension in other times. and understanding the importance of the relationship between these flat slab times and the more compressive segments and the generation of the major deposits in here, for example, in the Eocene Oligocene in northern Chile and southern Peru. And these were really important contributions, and there's many other examples I could have used here to show the same thing. But my question, if the goal of our model at this stage is the prediction of new districts, I would ask the question as to how predictive are those models at that sort of district scale within the overall broad arc. The other thing that people were doing at about the same time, here's an example from Jeremy Richards in the early 2000s, is starting to look at these structural controls, and it had been long recognised that we had the Dameco sort of corridor here in Chile, at least from El Salvador to Coyahuasi, etc., as a major control on major porphyry deposits. And then people started looking at the importance of these potential cross-arc features here, and we've all seen various maps of those in various arcs. And it's a very useful thought process, I think, but I think in my mind it's also still highly questionable as to whether it's really impacted on our ability to select areas at that sort of district scale. And then other approaches that have started to be developed more recently would be to look at ore deposits as forms of self-organised systems and look at their distribution along those major structural corridors. And an example here on the right from Nick Haywood and some colleagues, where they looked at the Laramide province in Arizona and northern Mexico, and looked at the major through-going corridors, such as the Silver Bell Cananea trend here, for example, well known, and then started looking at the distribution of the deposits along those, and made the case that there was a periodicity to the development of those clusters, and that the periodicity was likely to be related to the way in which the underlying magma chambers were formed, etc. So that starts to bring in an element of predictive capacity, I think, but I'd say it's still well and truly in its infancy. If we're going to get better at this sort of predictability, predicting districts within overall broader arcs, then the structural architecture is important. And here's a recent contribution from Jose Piquer and others in Chile, where they've looked at the structural setting of most of the major clusters in northern Chile, and have proposed the location of those in compressive segments of those broad through-going structures. And here's an example of the Gaby deposit in northern Chile, where the orientation of the deposit and the intrusions is here and almost normal to the orientation of the principal stresses. And it's these forms of studies, I think, that we really need, because there's been a dearth of really good quality detailed studies, I think, that have looked to understand the structural architecture of these arcs and use that as a way of predicting the location of new districts within the arcs. And staying at that sort of broad arc scale, and here sort of crossing a little bit of a line into the detection piece, but more recently we've seen obviously the importance of understanding magma chemistries. We had a great talk with Scott Halley in most recent GeoHug around detailed aspects of this, and I'm not going to go into it here, but I think the work has shown that there are characteristic geochemical signatures of potentially fertile intrusions. However, at the bulk scale, these tend to be able to define the prospective arcs and the prospective provinces, therefore, but we essentially already know that. So in some ways, the whole rock approach and especially unless there's blanket sampling, tends to tell us what we already know. So I think we need to be getting down into far more detailed scales, and this is some work here from Howard out at North Parkes. It's able to show the potential difference between intrusive phases within the same complex and be able to understand their the importance of the magma chemistry at particular phases in those particular short-lived phases within the intrusion, with the overall intrusion complexes, and that can potentially start to get us towards a predictive sort of stage. And in terms of the magma chemistry, I think we can get predictive, especially if we start to look at other mechanisms for understanding the magma chemistry that allow us to take a big picture sort of approach to that and allow us to sample large areas. And so here's an example. The graphs on the right are examples of detrital zircons from northern Chile, plotted on a number of diagrams that will be quite familiar to many people, particularly the Europium star diagram. But the critical thing here is that these are detrital samples taken during large-scale stream sediment survey programs that are actually potentially one tool that can start to allow us to predict interesting magma chemistries and therefore potentially interesting districts within broad parts of much larger arc segments. So if we move now to the evolution of that porphyry model at the deposit and district scale, and here, rather than area selection, it's all about navigation within the system, or within the district at least, and you know, simplistically from an explorationist's point of view, it's all about drill targeting, where we're going to put the next drill hole. And so I think these scale of models have implications all along the exploration life cycle. And many of you will be extremely familiar with the changes in this model over the years. And again, not every one of your favourite diagrams will appear in these next few slides, but it's to give us a sense of where the model's changed over years. So really the first of those sort of models that tried to describe the architecture or the nature of the system was the very famous Lowell and Gilbert model, which was extraordinarily useful, and I'm sure has been directly responsible for the discovery of quite a few deposits. We had contributions again by Dick Silito, starting to broaden that beyond just the sort of concentric sort of style of the Lowell and Gilbert model, looking at what the tops and bottoms of systems look like, so therefore an opportunity potentially to navigate in and around systems. And then the really seminal important work of Gustafsson and Hunt at El Salvador, I think, is an extremely important model, and was built on an enormous amount of work in a 3D environment, and again has been, I think, extremely useful in lots of discoveries. We moved on then through the 80s with a better understanding of what the tops of systems looks like, and they're starting to make those links to the high sulfidation and advanced argillic alteration to porphyry deposits. And then work at Yarrington from John Dillies and others started to give us a better sense of the overall architecture of a whole porphyry district because of the extended nature of the Yarrington district. And I think really important contributions in our understanding of alteration distribution, alteration facies from Jeff Hedenquist and others here. One of probably my favourite phase diagram here. If you understand that phase diagram, you understand most of the things about porphyry copper deposits. And they started to get built into our models. And then also really interesting and important work around the nature of the fluids at different places within the porphyry, overall porphyry realm. That allowed us to not only describe the zonation we're seeing, but starting to understand it as well. To the point where in 2010 we had Dick's what is probably still remains the sort of classic porphyry model here from his 2010 contribution, and you still see that in many company presentations and company websites. An extremely useful model. It is, however, at best a 2.5D model, and in most cases it's a 2D model, and we work in a 4D world. So this is one of the things I'll talk about in a minute. Things have still continued to move on, even though that 2010 model is the one we see probably most commonly. But subsequent to that, we've seen the work that's given us a sense of how to navigate within the lithocap environment from the temperature and geochemical zonation patterns we see there. For example, Xiaoshan Chang's work and others at Lepanto, far southeast. And then my equal favourite phase diagram from the really important work of Reed et al. At Butte, that showed us that the same fluid can be responsible for the generation of all of alteration facies we see in porphyry deposits. So if you haven't read that paper and you're into porphyries, then do yourself a favour and spend the weekend reading it, because it's a really seminal paper, and again, I don't think it's necessarily as widely known as it should be. To the point where sort of now these are maybe our classic models that people use to navigate in and around districts, and the one on the left from Dave Cook and others, and then Scott Halley and others on the right there. Extremely useful, and they're evolutions of those original Gustafson and Hunt, Lau and Gilbert models, etc. But again, I would argue that these are at best 2.5D and really more like 2D. So just to wrap that little section up, it's my view that the deposit and district scale models are pretty advanced and extremely useful, but that the belt scale models remain in their infancy. And I'd contend that despite being the most heavily researched deposit model in one of the most heavily researched deposit models, the model remains a very poor predictor at the deposit and district scale. And I'd argue that that's probably because that it's been a victim of its own success, in that those porphyry district and deposit models have been so successful at predicting where to go within systems, and they're easier in some ways to develop, because many studies of the geochemistry and the nature of those zoning patterns, etc., can be done from the laboratory and with box of rocks type studies, and don't need that hard work of getting out into the field and studying things at the big scale. So I'd say that, to me, that's one of the reasons that we've got really good deposit and district models, but quite poor belt scale models. So I just want to start to talk just to touch a little bit on a couple of examples of what's driven success and have our models helped, etc. One example, I won't go into these in detail, but one example where it's very clear cut that the standard porphyry model, who was a critical contributor to the success, is the Valeriano system in northern Chile, a Miocene age system that sits underneath a very large lithocap. And at surface, it's all advanced argillic quartz or alunite alteration, very large lithocap, sort of 10 kilometres by 5 kilometres or thereabouts. And it was explored for advanced high sulfidation epithermals with modest success. But what people started they used that standard model to say, we're in the lithocap, let's drill underneath it, pretty basic stuff. And as they did, they started to see the sulfide ratios changing with the occurrence of some chalcopyrite, and the chalcopyrite to pyrite ratio increasing in deeper holes. Also, the alteration started to change, and they started to see sericite alteration rather than the advanced argillic alteration, and critically sericidal alteration, overprinting early B veins there now. So that was a critical observation that was specifically able to be related to the classic porphyry model and encouraged them to drill deeper. And then lo and behold, when they did drill deeper, they found this fairly interesting potassic zone at greater than 1,000 metres depth, and some really interesting intersections, but it is at over 1,000 metres, so it's likely to sit there for quite a long time. But classic example of the standard porphyry model being critical to success. Another example of a recent discovery is the Saddle North deposit in BC, in the Golden Triangle. And I'd say here's an example where, rather than the porphyry model as such being important to success, it was just good quality traditional exploration work, geochemical sampling within a known district, so exploring within a known belt, but essentially the discovery of outcropping mineralisation here in the south, followed up by good quality geochemistry, and then geophysics IP and mags, and the drilling of the extension of those soil and rock anomalies out here into the IP anomaly. Here was the generator of the discovery holes here in 2018, and that project recently transacted at just north of $300 million, so a pretty decent success, but good quality basic exploration without really a lot of reference to the model. Another example, recent example that I think is a good example of where the model has again been critical to the exploration success would be the enormous Onto discovery in Indonesia, 15 million tonnes of copper, 27 million ounces of gold within a giant lithocap. So there's an 18-year exploration history here, so it wasn't something that happened overnight, but it was very much the standard porphyry model that drove the success here by just continuing to drill deeper into that lithocap environment to the point where they found unconventional mineralisation, covellite bearing, high sulfidation, copper bearing mineralisation within that giant lithocap. But without that standard porphyry model, they wouldn't have had the impetus to do that deeper drilling. And I've done a compilation here of a number of most of the significant porphyry discoveries in the last 20 or 30 years or so. And these are the ones where there's information available for. And what I've done is I've sat down, I've looked at the information and tried to understand whether what drove the exploration success. And the ones in green in the table here are those where it looks to me from reading the materials that there was elements of the porphyry model as it existed at the relevant time that were really critical to the exploration success. But these are the deposit and district scale models where people looked at the alteration distribution, sulfide distribution or whatever, and that drove was at least important in the success. I think there are also examples such as the Saddle North one that I talked about there, where probably less clear cut that the actual model was important in the exploration success, but all of them obviously the result of great work by dedicated teams, but really chasing geochem and outcropping or near outcropping mineralisation. What I don't see is evidence in those discovery histories of influence of that province or belt scale models in the processes. So my conclusion there is that I think those deposit to district scale models have strongly influenced and enhanced discovery success, and that also just empirical exploration programs with little reference to the model have also been successful. But I see very little evidence over that last 30 years or so of the influence of sophisticated, integrated sort of belt scale models, predictive models in the exploration success in the porphyry world. So to wrap up, a few directions. Are there any magic bullets, or are there any things that are going to lead us into this next discovery? And I wish it was always this simple. That hill there's the Pecoy breccia in southern Peru. Pretty easy to find on a day like that, but we don't always have God smiling on us like that, unfortunately. So I think in terms of future directions, why do we even need to change? What's wrong with what we've been doing? I'd say that we do need to change, and I say that we do need to get better. And one reason is that exploration maturity can only trend in one direction. It's impossible for exploration maturity to decrease. So by definition, in my view, exploration is going to become more difficult. And in more mature jurisdictions, success in exploration is likely to come undercover, as obviously we're seeing a lot of already, and by recognising overlooked opportunities. And I'd say the Saddle North is an example of the latter, but both of those with high quality predictive models, we can enhance our chances of success. I also think one of the reasons we need to get better is that land access is becoming more difficult. So the areas we have available for us to explore in mature jurisdictions as well as less mature and higher risk jurisdictions is becoming there's less land available to us. Environmental, community and other restrictions are increasing. So in my view, if we have these high quality predictive models, we can improve our efficiency of our area selection and avoid those unnecessary pitfalls of exploring in problematic areas. So one of the key developments that I think is underway, and all of you, I'm assuming most of you will be familiar with this, is that low detection limit whole rock chemistry and more readily available mineral chemistry has drastically expanded the detectable footprint of the porphyry copper deposits. So in that propylitic zone that we know and love, we're now able to navigate a little better in that, I think. And I think an important part of the story there is the demonstration that at least part of that contribution in the propylitic zone in some systems, or many systems perhaps, is actually a magmatic contribution. So that gives us a hope that we can actually navigate in there with the geochemical tools that we have available. And I think this world is in its infancy, but I think it's really going to start to have a strong influence, and obviously companies are starting to do that already. And it's an important refinement of the deposit and district model. And here's an example on the right from Dave Cook of their blind case study at Resolution, where their chlorite chemistry, the chlorite predictor was able to to indicate the potential location of the Resolution deposit. Now, I think there's a lot of complexity here, and I don't think we're there right now in terms of it being a lay down easy exploration tool, but I do think the expansion of the footprint by these new geochemical tools is really going to change our world. However, I would argue that our key failure of the current porphyry model is not at this scale, that it's the lack of predictive capacity at the belt scale. The other thing I think that's really changing our understanding of the porphyry model at the deposit scale is the collection of enormous amounts of mineralogical data, routine mineralogical data, combined with fancy analytical systems that have started to, I think, really revolutionise our understanding of the actual distribution of various phases within those porphyry systems. And the classic example being the green or grey sericite that anyone that's worked in the Andes will know and love. But we're seeing that that's actually a really complex story, and I think far more complex than the sort of traditional published models would argue or would suggest. And that is going to have, I think, an impact on our ability to navigate at the district scale. But I'll keep banging on that I think the key failure is our lack of predictive capacity at the belt scale, not necessarily at this scale. So what should we be doing about that? I think in order to address that gap, it really needs dedicated research at the appropriate scale. So we need to be thinking about that scale, and we need to be driving ourselves to the prediction of these districts. Essentially, this cartoon of Jeremy Richards, this is what we're trying to find in this belt scale predictive model, is these districts. Data collection principally by governments, yes, at the appropriate scale, is probably one of the biggest things that can help here. Unfortunately, most governments are not collecting that data. Australia is obviously a standout here. I would argue, unfortunately, our tectonics don't really help us for too much there on the porphyry front, but Australia is certainly a standout in terms of the types of data collection we need to flow into these models. But I think companies can and are filling the gaps with these regional data collection, and that's critical. I think the integration of the various strains of things that contribute to the porphyry model is where we will see these step changes. And I believe that many companies are actually already doing a lot of this. It just doesn't make its way out into the public domain. So therefore, I'd say that greater collaboration between those companies and various research institutes for mutual benefit could certainly accelerate our generation of a really robust integrated model. And companies can push for and fund appropriate belt scale research from the research institutions. And I think a big shout out here to BHP and the Bristol Uni folks in terms of what they're doing in that sort of integrated approach to their porphyry models. And I'd really love to see us move beyond cartoons. I mean, we're a four-dimensional science. We have lots of fancy communication tools available to us at the moment, but most of what we see and most of what we use, unfortunately, are still two-dimensional cartoons. So with that, I'll open up for any questions.
You're welcome, to jump off mute or use the chat if you've got any questions or comments at all. I can see David Wood, did you have something?
Hey, Stu, great talk. Thank you. Question for you. So that area selection problem is not unique to porphyries by any. I mean, it's the industry-wide, commodity and deposit style wide. Where do you put your best square within your call it province or region, at which point you start spending real money on new data acquisition, in particular around drilling. But would you say, I mean, the Porphyry model is probably more predictive in that sense and more advanced in terms of being able to put that box on the map compared to other deposit styles? Would you agree with that?
No, I don't, to be honest. I think other deposit styles are probably a little more advanced around that piece. And I think part of the problem we have in the porphyry world is that deposit and district model has been so successful. And I think that's because porphyries have large footprints. So we can go and we can study the alteration, and it's that sort of kilometre scale, and we can effectively zone into it. I think if you look at the nickel world, magmatic sulfide nickel or diamonds, for example, where the deposits don't have these big sort of alteration footprints, geochemical footprints, they've had to focus a bit harder on understanding those key geodynamic controls and the key controls on the location of their deposits. So I think they're probably further advanced than we are in the porphyry world, because we've had the advantage of these enormous hydrothermal systems that are often easy to see, such as the top of Valeriano here.
Would you say, but I mean, in terms of prediction of, so there's within any belt and arc segment and regional province that's got porphyries, there's multiple magmatic hydrothermal systems, multiple porphyries, but not all of them have superior grade development. I mean, that would be the thing you'd want to predict, is not just a porphyry, but a high grade porphyry.
Yeah, I think you want to predict that if it's undercover. Your first goal is prediction of a district, a potentially fertile sort of magma chamber that might be throwing off porphyries, I think. If you actually have the system and have parts of the system that you can actually sample, then I think you're at that stage of, trying to, as quickly and as cheaply as you can, predict the potential fertility of that system. And obviously, if that's undercover, you've got to drill a few holes into it. But to me, I think that the key area selection puzzle is around the prediction of districts within those broad 100 million year, 1,000 kilometre kind of scale arc environment.
Thanks, Stu.
Excellent discussion, Stu. I've just got a couple of quick comments. Totally agree with the 4-acid digest and the whole rock geochem stuff, and combining that with core scan, the way that Scott Halley's doing that, using AI and IO gas, those things, they are the tools of the future to help us hone in on our porphyries. But another new technology that I think we're about to start seeing a whole lot of is low-level geophysical stuff using a UAV. So getting those little UAVs with 4 or 5 little propellers on them that fly around with a little low-level mag, getting some really tightly spaced, low-level detailed magnetics is about to become really dirt cheap, and it's going to open up the world for structural interp and zoning in on those magnetic signatures of intrusives that are often related to porphyries.
Yeah, I think you're right, and I sort of deliberately stayed a little bit away from those detection pieces. But you're dead right. As things get cheaper and easier to do, then we're going to get better at predicting, as long as we make sure we don't miss that piece of sort of integrating those with all the other data and the other advances. But yeah, I think we're in a really interesting time at the moment in the porphyry world.
Yep. Thanks.
Stu, a couple of questions from me. Great talk.
Thanks.
Oh, just looking at that Titley and Bean map and the USGS, it's quite a telling map, isn't it? I mean, we really haven't found too many belts, as you say, in the last 40 years, new belts. And then we get down to the belt scale, and we know there's a lot of the obvious alteration zones have been drilled. You'd have to say, right? So at least in the 9 belts, I guess there are examples of some frontier exploration still taking place around the planet, but there aren't too many of those. Ecuador, I guess, has been one pretty good success of late, and I guess, as you say, there's some examples in Asia of new discoveries, but they are getting harder. There's no doubt about that. So is it just a question of going back to the same old belts, and looking deeper? Is it that simple?
That's certainly one thing that needs to be done, and you're looking there right now at an example of one place where I think that can work. So the Miocene in Chile, for example. So the Valeriano system sits at 1,000 meters, but there's probably other porphyries of similar age that may sit closer to surface, and certainly not all of those have been drilled. Some have. So I think there's examples where you do need to go. You simply use the traditional model at that sort of deposit district scale, and be prepared to go deeper. And the Onto example, it's not in a super mature environment, but just being willing to drill deep there and been rewarded by the sort of grades that they're seeing there that are potentially economic. I think there's also opportunities for the discovery of districts within relatively mature belts. Obviously the classic thing being undercover, but also where the footprint of that district is not right at the current observable surface. So again, it's a bit of an example of going deeper, and I think that's the way of the future in more mature belts. And then if you're investors, if you have the risk for the appetite for the higher risk countries, then you go to those countries where things potentially can be still sticking out of the ground.
Yeah. We've had some in the chat. So I guess the power of deposit models is the ability to vector within expressions of hydrothermal systems. The power of the belt scale approach is in showing the large tracts with potential. The real challenge is the missing link in which areas inside the belt, thanks to structural and magmatic controls, have potential to develop a porphyry, and how fertile is that likely to be? Besides zircon chem, is there any ideas on where you'd focus research to address the gap?
Yeah, I think the thing that intrigues me is that the fertile systems and the fertile districts are very short-lived periods within overall longer-lived magmatic arcs. So things that can help us to understand and predict that fertility within those long arcs, I think. So, the mineral chemistry, and there's zircon chemistry, there's other minerals as well that I think can be very useful there. It's then about being able to sample them at enough density that they can actually be useful at that sort of belt scale. So I think what some companies have started to do now, using that stream sediment approach and even sampling zircons in gravels, etc., in northern Chile, for example, is one way that we can actually start to use that sort of chemistry to zoom in to districts that are otherwise are not expressing very well. I think also just understanding the fundamental architecture of these arcs from a structural perspective, and where have been the favourable places to have in place those fertile magma chambers, given them time to do their thing in the subsurface. And so understanding those key structural controls, I think, is still really quite poorly understood in many places. It's limited in places by the data available, but as someone pointed out there, maybe we're about to see new waves of data that'll start to allow us to generate those interpretations that can really help us predict those new districts within those belt scale environments.
Stuart, how would you respond to the suggestion that by the time we understand the belt well enough to perhaps start to have deterministic models of where a fertile porphyry might be, we've pretty much found them all by prospecting, and our search space has disappeared?
Yeah, it's an interesting question. I mean, we clearly, as belts become more mature, we learn more about them, but the search space and the residual potential diminishes. I think we can come sort of halfway there, in that early on in the in the exploration of belts or regions, if companies or research institutions or governments take an approach of really trying to build those fundamental data sets to understand early and as quickly as possible, then I think you can potentially start to use that predictability before the search space disappears. So I think there was opportunity, for example, in countries like Mongolia or etc., as that was opening up to do that sort of work, and I'm not close enough to it anymore to know if that's still an opportunity. Here, even in the Miocene of Chile, I think there's still enormous potential for porphyries there, but we need to think about going to that next sort of level down. But I do agree with what you're saying. It's a challenge, but we just got to make sure we're building our models faster and better than we have traditionally in the past.
And does the neatness of the porphyry model lead enthusiastic explorers to over-drilling of low-grade systems or drilling at impractical or difficult depths?
Great question. I'd probably suggest it's the over-drilling of poor systems, probably driven more by investor sentiment and the state of the markets at any given time than the model. I think well applied, the model is sufficiently predictable that it improves your chances of success. So I think those examples where people have over-drilled really rubbish systems are probably examples of a poor application of the model, driven in some cases, I'd say, by investor sentiment and market hype at while we're in periods such as we are now.
Yeah. Not yet.
I think one of the problems we have as an industry, of course, is that, if you don't have success in your first round, given whatever approach you choose to take, then it's tough to convince your investors, whether they be the CEO of a big company or whether they be the equities markets in Toronto, that it's hard to convince them to allow you to have another crack with a different approach.
That's very true. The price of failure is usually obscurity. Nobody says, "Oh, well, you must know more now than you did when I backed you last time."
And that's where the opportunity, I think, Dick Silito says it's generally the fourth explorer that finds the deposit in any district. I think that's where the opportunity lies. If you're one of the subsequent people, is to take the data of the people that have been there in the past, look at it with different eyes, and then you can be successful on that front. But I hope most of us don't end up then going around bagging the people that were there before, because it's a tough business that we've chosen to be part of.
I'm so appreciative that you've come on, so thank you so much, Stuart.
No, thanks everyone. Thanks to you, Jess, for making this happen. Fantastic initiative, and thanks to everyone for your interest. And hopefully, with many of you, we'll be able to have this conversation over a beer one day and do it properly.
Definitely.